sitting here 45 minutes. I can't get anything.
All right. Well, it's a new day. It is Wednesday. I think this is actually the second. Now this marks the second half of the class. Actually, you're halfway done with circuits already, and I have to admit I'm excited too. Um, Except I believe somehow the schedule got changed around and they took me off of 3170 for the fall and I get to teach circuits again in the fall. Yeah. I don't know how that happened exactly because that wasn't the plan, but whatever. In the way of announcements, I did put up a homework assignment like just before I walked over here. But what I did is I put in the material from Chapter 6 and Chapter 7 that we're starting to cover now. And so I wouldn't imagine that this homework will be due until maybe Thursday next week kind of time frame. So, and there's just a couple of questions, fairly straightforward ones from Chapter 6. So you can get started on it and be ready to go as just keep up with the material and you should be ready to turn it in nice and soon. We do have a quiz at the end of class. Online students should be ready to go. I think I do have one more thing to do for that, but what else? I will post homework solutions to the homework that you turned in yesterday, grade that today, and get it back to you tomorrow. So, are there any specific questions on anything? Are there ever questions on anything? All right. So, to go back and start talking about the things that we covered yesterday, we started talking about these first and second order transient circuits. And in other words, starting to integrate some circuits or integrate components into the circuits that we haven't dealt with before, putting inductors in, putting capacitors in, and getting some sort of understanding as to how they affect the circuit. So we're going to start out with simple circuits that just contain a single storage element of some kind, and then we'll move on to second order circuits. And each of these are so named because the solution to the first order circuits is a first order differential equation. The solution to a second order transient circuit is a second order differential equation. So you can solve them that way. There's some information in the textbook on how to do that, but the step-by-step method that I learned as a student and what I teach, I think is a little bit more interesting. But so we use the camera flash as a quick example of how all of this stuff comes about. You've got a capacitor in there, and the battery charges up the capacitor. Then the capacitor discharges very quickly across the flash to get you that burst of light instead of having the flash light up nicely for several seconds and then die out. So it discharges very quickly. And then you can hear that kind of whining sound as the capacitor charges back up. And we can quantify all of that behavior. Mathematically, we can show that you get this differential equation, and the solution to that fairly straightforward version of the equation is that V0 e to the negative t over tau, or negative t over RC, where the R is the value for the flash resistance itself, the C is the value of the capacitor, and what it basically says is that the voltage across the capacitor drops as this decaying exponential. With a controlling constant of 1 over RC, essentially. So that's, and generically speaking, then we find that all of these circuits will fit the nice first order differential equation of the form K1 plus K2 e to the negative t over tau, which is the particular and characteristic solutions for the differential equation itself. So the step-by-step method that we're going to continue to use as opposed to the differential equation method is pretty straightforward. We're going to always assume that the form of the solution is that K1 plus K2 e to the negative t over tau. For all the circuits that we'll look at, that's going to be a perfectly fair assumption. And the bullet says x of t, and what that's indicating is that this is going to be the form of the solution for any voltage or any current parameter within the circuit. And that could even be the voltage across the storage element itself, the current through the storage element. That's an interesting enough problem in and of itself. But that's going to be our assumption, is that the solution does take that form. Then we're going to assume that the circuit has been in its position before the switch is thrown for long enough to have achieved a steady state condition. And as we saw yesterday in our first capacitor example, the amount of time it takes for it to reach that steady state condition, it was a whopping 3/4 of a second. So it's not an unreasonable assumption to think that the circuit could be at steady state. So what that means, going back to the chapter 6 material, is that all of your inductors become shorts and all of your capacitors become open circuits. And then we're going to solve for a parameter describing parameter revolving around that storage element. And that's going to either be the voltage across the capacitor or the current through the inductor. The reason that we do that is, going again back to chapter 6, we found that the voltage across the capacitor cannot change instantaneously, or else the derivative would have a value of zero, or a value of infinity, and that would in general be a bad thing. And so what happens is that even though the switch closes, we can't have the voltage across the capacitor changing instantaneously or the current through the inductor changing instantaneously. And so those things will continue to put forth that amount of voltage or push that amount of current. And so what we'll do is, once we've found that initial condition on the storage element, we're going to replace the storage element with an independent source. It'll be a current source for an inductor. It'll be a voltage source for the capacitor. And the value for those sources will be whatever you solve for in step 2, whether it was the voltage across the capacitor or the current through the inductor. And then you solve for the initial value of your desired variable, the current, the voltage, or whatever. And we're going to give that the name I of 0 plus or V of 0 plus, whichever it is that you happen to be solving for. Step 4 then is to redraw the circuit and take a look at now that we've established a steady state condition again with the switch in its new position. At least 5 tau time units have passed, whatever that happens to be, and that, for all intents and purposes, could be infinite and an infinite amount of time, because the circuit will settle down in a certain period of time and stay there. And once you get past 5 tau, you're like 99+% of the way to that steady state condition. So it's a fair estimation to do it that way. So the inductors become short circuits again, the capacitors open up again, solve for your final, the steady state variable, I of infinity or V of infinity, whichever it is that you're looking for. Again, using the steady state circuit, find the Thevenin resistance from the terminals of the storage element. That's a key thing. You're always looking from the terminals of the storage element and not from the terminals of a resistor that you might be finding the voltage through, or the current running through a particular resistor. Don't look at that resistor. We're looking from the point of view of the storage element. And since it's a Thevenin resistance, we're going to short circuit our voltage sources. We're going to open circuit our current sources. And we'll get into this today, if we have a circuit that contains dependent sources as well as our storage elements, then we have to solve for the open circuit voltage and the short circuit current, and then that will give us our Thevenin resistance. So, this can get to be a fairly long process, to be honest. So what does the Thevenin resistance give us? Well, it gives us part of our time constant. We're going to multiply that Thevenin resistance times the capacitance, or we're going to divide the inductance by that Thevenin resistance to get the time constant tau, which will stick up in that in the denominator of the exponent. the two constants K1 just equals x of infinity, and then K2 equals x of 0 plus minus x of infinity. And that'll give you your final form of the solution. So that's the process. It's maybe a little convoluted, but for the most part, it shouldn't be too bad. And I think that it really shows me, from my point of view, when I look at your work, if you're understanding the way that we do this, all of these circuit analysis things. So we did one example yesterday with a capacitor. We went all the way through. So we solved for the initial voltage across the capacitor, placed it with voltage source, did all of the rest of the stuff. Today what we'll start off with is an inductor example instead. And I hope that I can follow my notes because I have a bunch of stuff scribbled out and I hate when I do that. But anyways, here is a first order example with an inductor in it instead. So here is our circuit. So there's the circuit itself. Here's the switch. It closes at time equals 0. The 2 ohm resistor over here, a 1 ohm resistor here, a 4 Henry inductor here, 12 ohm resistor here. This is a 4 ohm resistor, and the component that the parameter we're solving for is what is the voltage across that 4 ohm resistor. We've got a 6 ohm resistor here and a 24 volt source over here. So these are ohms and not kilo ohm resistances. But that's the original version of the circuit, either way you look at it. So the first step is solve for the current through, assume that it takes the form that we had talked about, K1 plus K2 e to the negative t over tau. And then we need to solve for the initial condition of the current as it's running through the inductor. So here is a current IL, and that's going to be the first thing that we want to solve for. So first thing that we need to do is kind of draw the circuit at steady state before the switch closes, so that we can make sure that we do this right. So we've still got that source. I'm going to try to draw this a little quicker. This is a short. This is still open because the switch hasn't been closed yet. And we've got that and that. Now technically, it is worth noting that that resistor is there, but it's been shorted out by the fact that this inductor is behaving as a short under the steady state conditions. So you can kind of draw it in as a dashed line or something, but realistically there's not a whole lot going on. So that's the 1 ohm resistor. This is the 2 ohms. This is 6 ohms. This is 4 ohms. This is 24 volts. And so we're just solving for the current I sub L as it runs through that loop. This shouldn't be one of the world's scariest kinds of circuits to look at. The way that, how might you attack this one? There are at least a couple of different reasonable ways to do it.
I'm current across 4 and 6 ohms, and you can subtract the 6 ohms from the 4. Or I sub L.
Yeah, I think what you're getting at is, all right, let's take this, the 1 and 2, combine those and get this down to a single loop circuit, find out what the current is, maybe call it I0 that's running through here, and then figure out how does that I0 divide across the 6 and the other resistors over here. Yeah, that's a pretty reasonable way to do it. There's nothing, no problems with that. Another way you could do it if you felt so led is you could say, well, let's do a single nodal analysis. You can do it with one equation, v1 minus 24 over 4 plus v1 over 6 plus v1 over 3. Solve for V1, and that will give you the voltage across the 6 ohm resistor as well as the voltage across the 3 ohms of series resistance there. Both of those are reasonable ways. The way that I have it in my notes is actually the first way that was suggested. So we have the 3 ohms of resistance here, the 6 ohms here. Those are in parallel with each other, and we can combine those into a single 2 ohm resistor. So the simplest version of this circuit, we've got the 4 ohms and then 2 ohms and 24 volts. So we do a simple voltage divider. That's 24 times 2 over 6. And what is that? A third of 24 is 8, right? So that's 8 volts. So there's 8 volts across the 6 ohm resistor, and there's 8 volts across, there's 8 volts across the 2 ohm parallel resistance, equivalent resistance, which means that there's 8 volts across the 6 ohm resistor. There's also 8 volts across these 2 resistors in total. So the current IL would just equal the 8 volts divided by the 3 ohms of total resistance. So 8/3 of an amp. And again, since we're not dealing with kiloohms of resistance here, we're dealing with tens of ohms, or ones of ohms, I guess, for the most part. And so nothing surprising there. You'd find the same thing if you did the nodal analysis. You'd find that V1 was 8 volts, whatever. So that's step 1. I guess that's step 2, right? So the next step then is we take what we learned in terms of that 8/3 of an amp current, and we stick in a current source where the inductor was, and show the circuit with its new configuration. So we've still got the 24 volt source. That didn't go anywhere. We have the 4 ohm resistor. That's the interesting one to us anyways. We've got the 6 ohm resistor. We've got a current source of the value of 8/3 of an amp. This 12 ohm resistor comes back into the picture as a result of the inductor no longer behaving as a short circuit, at least. So it kind of comes back into the picture. And then the switch has been closed. And so effectively that 1 and 2 ohm resistor on the far right hand side of the problem, again, they're shorted out, and they really don't play into the picture at all anymore. They just don't. So you can go ahead and ignore them pretty safely. So we need to solve for the voltage here. The way that I have it done is as a nodal analysis problem on my notes. So we'll go ahead and do it that way. Yeah. Otherwise, it'd be kind of nasty. So just let's see if we can do this in an intelligent way. Because the way that I actually have it in my notes is I put another node V2 here, but this is really the reference node, as I would write the rest of my nodal equations. So I'm going to try not to write that and make sure hopefully I'll get the same answer here. So we've just got one equation to write. We've got, coming out this branch, we have V1 minus 24 over 4. We've got V1 over 6. We've got V1 over 12. And we've got a positive 8/3 of a milliamp. or sorry, 8/3 of an amp that are coming out of that. So that should be all of the 4 branches. That should sum to 0. So to get rid of all of the denominators, let's multiply everything by 12. That gives us 3v1 minus 24 times 3. Is that 72? Yeah, I think that should be right. Minus 72 plus 2v1 plus v1 plus 32 equals 0. So we've got, this is a total of, what, negative 40. So we put positive 40 on the other side. And we've got 3, 5, 6 V1 equals 40. So V1 equals 40 over 6, which is 20 over 3. And that does work out. That's the same number as we ought to get, I suppose, for the node voltage V1. But don't stop there. That's not quite what we're looking for. We're looking for the parameter V of 0 plus, which is given the polarities is the difference between the voltage at this point and the voltage at this point. The voltage at this node is given as the 24 volts. The voltage at this point we just solved for as 20 over 3 volts. And that gives us the lovely quantity of 52 over 3 volts. Whatever that happens to be in terms of a fractional number. Obviously, it would be irrational because it's over 3. Well, I guess it just would be, it's not irrational, but it doesn't terminate nicely. What's the real mathematical name for that? When the fraction doesn't have a nice closed form, like 1/3.
When it can't be expressed as a big fraction.
Yeah, when it can't be expressed as a real a nice fraction, it's irrational. But when you can't express a fraction as a closed form decimal number, there.
Is it the same thing?
Is it? Like 1/3 doesn't have, you can't just say, like what is 1/3 is 0.3 repeating, right? Isn't there, I thought there was a fancy mathematical name for that. Probably is. I guess you go next door and you find out what that is. Anyways, the point of all of that, I suppose, is that we've got our first parameter. That's the value of V0 plus, which is the value of 52 over 3. So now we take a look at the circuit at time equals infinity, or at least time. So this is the circuit at time equals 0 plus. So now we look at the circuit at time greater than 5 tau, which is, more or less the same as time equals infinity, because this behavior of the circuit is pretty much the same. This is where things can get kind of odd, to be honest. So we've got the 24 volt source that doesn't go anywhere. We had our 4 ohm resistor, and here was our 6 ohm resistor that was hanging out before. Here's where the inductor was. It's now acting as a short circuit again. Here's where the switch was. It's closed. Here's that bottom node again. The 1 and the 2 ohm resistors, which were over here originally, we already decided they've been shorted out. That one they don't really affect their circuit anymore. And this 12 ohm resistor that was up here, well, that's actually shorted out again too, just like it was at our time equals 0 minus analysis of the circuit. But actually, that 6 ohm resistor is also shorted out. And so where does the 24 volts have to go but to the 4 ohm resistor? Nowhere. So with our very in-depth analysis, the value of V at infinity is simply 24 volts because it doesn't have anywhere else to go. Now, it's fair to do that and to kind of eliminate all of those resistors from your analysis as when you're solving for the voltage or the current. That's fine. But when you start looking at the Thevenin equivalent, you can't just totally ignore all of the resistors in that same way because the behavior is not going to be the same. When you take out the short circuit and you say, here's where my inductor was, and I'm looking in from those terminals to find the Thevenin resistance, now I can't just ignore the fact that, well, there was a 12 ohm resistor up here. And there is a 4 ohm resistor over here. There was a 6 ohm resistor here. I can still safely ignore the 1 and the 2 ohm resistors which were over here because they're still shorted by the switch. But this was 4, this was 6, and this is 12. This one you have to, again, this is one of the worst things for me personally. I know that mechanical engineers have to take the spatial visualization test as they come into the university, and I know that I would just out and out bomb that exam. I have no spatial visualization skills. And so it takes me a lot of analysis to look down at this and say, look, all of these resistors are connected at that node, and that, well, these are obviously in parallel. That one's pretty clear, but this node is this node is this node, and so they're all connected in parallel. And that is hard for me to see if I'm not really thinking about it, to be honest. So, but be careful and analyze it the proper way. Make sure that you pull in all of the appropriate resistors. When we did the analysis at t greater than 5 tau, the 6 ohm resistor was shorted, the 12 ohm resistor was shorted, and so, but that doesn't mean that as we get to the Thevenin equivalent that all of those resistors are also similarly shorted out. So be aware of that when you do that. Don't assume that too much stuff disappears. So the equivalent Thevenin resistance is 1 over 6 plus 1 over 4 plus 1 over 12. And cheating, that's 2. Again, that's not quite everything that we need to do with the Thevenin resistance. The whole point of solving for it is to solve for tau, and that is given as L over R Thevenin. It was a 4 Henry inductor over a 2 ohm resistor, which gives us a time constant of 2 seconds. Interestingly, this circuit takes a little more closer to 10 seconds to settle down. And so it would have to be at its steady state for 10 seconds before the switch was thrown for this analysis to be meaningful as well. So let's kind of put together all of the stuff that we ought to see. We know that, let's see, V of 0 plus was 52 over 3 volts. V of infinity was 24 volts. And tau was 2 seconds. So K1 simply equals, that one equals V of infinity, and that's 24. K2 equals, that's the V of 0 minus the V of infinity. I think that's right. And so that's 24 minus 52 over 3, which should give us negative 20 over 3. That must be the other way around. Yeah. 52 over 3 minus 24. Make sure this is... Yeah, that looks right. Yeah. It helps if you put the parameters in the right order. So yeah, that equals negative 20 over 3. And our final form of the solution then will be v of t equals k1, 24, plus k2, which was a negative number, so just say minus 20 over 3 e to the negative t over 2. And I guess technically that is a voltage. Look reasonable? Yeah.
Do you have to write 10 with the time constant, or do you write 2?
What was that?
In the equation, the final equation, when you write the final equation, do you write 2 or you write 10? Because after 5 seconds, that's when the
You write 2 because it's tau that actually goes into that spot. If it asked, if the question happened to ask how long does it take the circuit to settle down or something like that, you can then you would write 10 or something. But the form of the equation that we're working with is k1 plus k2 e to the negative t over tau, and not e over, or the negative t over 5 tau. So you put 2 in there. All right, so why don't you guys try one? It's not too nasty of a problem, I think. So there you go. There is the circuit. Apologize for the kind of tiny little voltage source here, but you got the 12 volt source, 1 ohm resistor, 2 farad capacitor, 2 ohm resistor. The switch is closed initially and opens up at time t equals 0. You got this 2 ohm resistor, the 8 volt source, positive terminal at the top, and what you're looking for is the voltage V sub 0, which is across the 2 ohm resistor. So as you go, the first step is assuming that it will have the form of the solution that we've been working for. So the first step that you need to do, solve for the initial voltage across the capacitor at time equals 0 minus. Solve for V0 of 0 plus. Solve for V0 of infinity. Find R Thevenin, and then put it all together. So give it a go. I'll give you about 5 minutes or so to kind of work on that one. And we'll come back together and take a look at the solution. All right, so let's take a look at what's going on here. And I've got it all worked out. We'll just kind of walk through it, and you can verify your arithmetic in the way that you, the answer that you got as you went through. So when our first step, solving for the voltage across the capacitor at time equals 0 minus. This is what the circuit looks like. The switch is closed, and so we've got a couple of sources, we've got a couple of resistors, fairly straightforward. The way that I chose to solve it was to do a mesh analysis to find out what the current was. We'll find out what both of the currents are, but in this case, as I've written them, we've got this one being I1, this one being I2. And so going around the first loop, we have negative 12 plus 1 times I1 plus 2 times I1 plus 2 times I1 minus I2 plus 8 equals 0. When you simplify that all down, you get 5I1 minus 2I2 equals 4. Going around the second loop, we've got negative 8 plus 2 times I2 minus I1 plus 2 times I2. Simplify that to negative 2I2 plus 4I2 equals 8. Solve those two equations simultaneously. You should get that I1 equals 2 amps, I2 equals 3 amps. And so the actual voltage around the capacitor, across the capacitor as it's open circuited at the steady state condition, if we're careful and we write all the polarities of voltages around this little loop, we've got negative 12 plus 1 times I1 plus VC equals 0. Solve that for the voltage across the capacitor, and you get 10 volts. So that's the initial condition. The voltage across the capacitor is 10 volts. So the next step is to take and open up the switch, stick in our 10 volt source, and do the analysis for the parameter that we're looking for, which is eventually going to be that voltage across the 2 ohm resistor on the far right. You with me so far? All right. So here is what that circuit looks like. We've got the 12 volt source originally. We've got the 10 volt source, which is standing in for our capacitor. And when the switch opens up, realistically, all of that stuff in that branch of the circuit goes away. It just doesn't affect the circuit anymore. You can, and I actually did in my notes, go through a whole nodal analysis to solve this, but it's really unnecessary because we know that the voltage around the closed loop here is going to be, will sum to 0, or if you just kind of, and it'll be okay to do this because, but it's fine to do it anyways, is that the 10 volts that are across this will be evenly distributed across the 2 ohm resistors. So you'll have 5 volts across this one, 5 volts across that one. The work here, V0 equals 10 times 2 over 4, is a formal voltage divider for that. But as you might expect, it divides evenly across the 2 resistors. And so that's our second component, that V0 at time 0 plus. So this is a circuit at time equals 0 plus, is 5 volts. Step number next is redrawing the circuit now that everything is kind of settled down. The switch is still open, so all of that stuff in that branch is gone. The capacitor is now open and acting as an open circuit again, so it's essentially gone. And finding out the voltage around here, again, you can write a KVL equation around the loop if you wanted to find out what the current actually is. If you did that, you'd have negative 12 plus 1 times I plus 2 times I plus 2 times I. Ignore that subscript, equals 0. Or 5 times I equals 12. So I equals 12/5 of an amp. And the voltage V0 equals I times 2, which is the same as what we got down here. 2/5, or it gives you 24/5. And that is our voltage at V infinity, but we're just going to, realistically, this is just time greater than 5 tau. So you should get 24/5 for that one. Now doing the Thevenin resistance. This is one where, again, you need to be careful because depending on where you look into the circuit, the these resistors will be in a different configuration. You almost want to look at it and say, well, gosh, all of those are just in series, right? Well, not from the point of view of the storage element. From the point of view of the storage element, here's a node, and so these two are still in series. The two 2 ohm resistors are in series, but that pair is in parallel with the 1 ohm resistor. So finding the equivalent Thevenin resistance is 1 over the reciprocals of those two resistances, which numerically works out to be 4/5 of an ohm. And so then we use that to solve for the time constant tau, which is our Thevenin times the capacitance. The capacitor was 2 farads. We had 4/5 of an ohm of Thevenin resistance, which gives us a time constant of 8/5 of a second. So, you know, easily enough, the circuit will settle after 8 seconds total, if the question were to ask you for that or something. And we put it all together. K1 is just equal to that voltage that we solved for at time equals, or time greater than 5 tau, which is 24/5. K2 is the difference between the initial voltage at time equals 0 plus minus the time at greater than 5 tau, which gives us 5 minus 24/5. This one is 25/5. So 25/5 minus 24/5 gives us a single fifth left. How many of you are ready for a fifth right now? Oh, most of you, okay. And you put all that back into here, and so you got the final form of the equation is 24 over 5 plus 1 over 5 e to the negative t over 8/5, which can be written in a slightly nicer way of 24 over 5 plus 1 over 5 e to the negative 5t over 8. Not too bad? So that's the process, and at least for any circuit containing just independent sources, that will always be the same. And there's a few questions on the homework that ask you to start looking at that. And any of the circuit analysis techniques that we've talked about will always be fair game for analyzing these circuits, whether it's nodal analysis or mesh analysis. I can't think of a reason why you would want to do a Thevenin analysis, but you could. You can use superposition, you can use linearity. Any of those things can be used to solve for any of these parameters, the voltage across the capacitor, the current through the resistor. You know, all of those things are all fair game, and it's just a matter of trying to choose what is the most appropriate one for the parameter that you're solving for, what's going to give you the easiest answer. Trying not to write supernode equations if you can help it, or whatever else. And yeah, so what we will look at tomorrow, I don't want to try to get into it to make sure that you have plenty of time to work on the quiz today, is what you do when you start getting dependent sources, because again, if you should remember, and what you should be ready to do right now, as a matter of fact, is that when we're finding the Thevenin resistance for a circuit that contains both independent and dependent sources, we need to find the open circuit voltage and the short circuit current in order to find out what and the ratio between those gives us our Thevenin resistance. So that is what makes first order circuits with dependent sources kind of difficult, is that we have to do both of those steps as if it wasn't a long enough process as it is. So we'll take a look at those tomorrow, which will also then get us into second order RLC circuits, which, yeah, those can be very confusing, but they also can be relatively well understood if we look at them with kind of a cookbook method. And in this case, we're going to deviate slightly from the textbook, because I don't think anybody in this department actually likes the way that our textbook does that material, but whatever. So any questions before I hand out the quiz? All right, let's do this, and we'll see you tomorrow.